Hey everyone, and welcome. Have you ever wondered how engineers can predict exactly how a skyscraper will sway in the wind? Or how an electrical circuit is going to handle a sudden power surge? Well, the answer is in the math that helps us tame all that chaos. We're talking about second-order non-homogeneous differential equations. Basically, they're the key to understanding how systems behave when they're being pushed around by outside forces. So let's dive in. Let's start with the big picture. Just think about a bridge, right? It's got traffic rumbling over it all day long, or a circuit with a steady voltage coming from a battery. These systems are never just sitting still. They're under constant external pressure. So how in the world do we model that? How do we predict what's going to happen? That's the exact puzzle we're going to piece together today. To get there, we first have to speak the right language, the mathematical language that describes these forced systems. This is where we get to peek behind the curtain and see the engine that drives all that real-world action. And here it is. This is the equation we're going to be working with. Now, that whole left side, that describes the system's own internal dynamics. It's a natural way of being. But the real star of the show today is that little guy on the right, the g of t. That function, that's our external force. It could be the wind pushing on the bridge, or the vibration from an engine, anything. And when that g of t is not zero, we say the system is being forced. And the equation is called non-homogeneous. Okay, so how do you solve something like this? Well, it turns out there's this really beautiful and logical strategy. Instead of trying to tackle the whole thing at once, we're going to break the problem down into two much more manageable parts. And this right here is the central idea, the total solution, the complete picture of the system's behavior. Y of t is simply the sum of two different functions, y sub c and y sub p. What this does, and this is the brilliant part, is it separates the system's behavior into two stories. Its natural internal response and its specific response to that outside force. Let's break these two parts down. On the left, we have y sub c, the complementary solution. Think of this as the system's personality, its natural behavior if you just left it alone. This part contains those arbitrary constants, c1 and c2, that let us adjust for the starting conditions. Then, on the right, you've got y sub p, the particular solution. This is the system's specific, dedicated response to that external force. And here's the crucial difference. It has absolutely no arbitrary constants. It's just one specific function that gets the job done. All right, that's enough theory for now. The best way to really get this is to see it in action. So let's jump into a concrete example and watch how this whole two-part strategy plays out. Okay, here's our first problem. We've got a differential equation. And you can see that the forcing function on the right, our g of t, is 2 times e to the t. Our job is to find the general solution that describes everything this system can do. And we're going to follow a super clear 3-step plan. First, find the system's natural behavior, that y sub c. Second, find and check the specific response to the force, y sub p. And third, you just add them together for the final answer. Simple as that. Step 1, the natural behavior. To do this, we pretend the force isn't there, so we just set the right side to 0. This gives us the characteristic equation, r squared minus 5r plus 6 equals 0. A little quick factoring gives us r minus 2 times r minus 3, which means our roots are 2 and 3. And just like that, we have our complementary solution. Y sub c equals c1 times e to the 2t plus c2 times e to the 3t. Done. Now for step 2, we need to check the particular solution. Let's test out the function y sub p equals e to the t. Well, the great thing about e to the t is that its first and second derivatives are also just e to the t. So we can plug it straight into the left side of our equation. We get e to the t minus 5 times e to the t plus 6 times e to the t. Let's see, 1 minus 5 plus 6, that gives us 2 times e to the t. And what do you know? That is a perfect match for the right side of our original equation. It works. And now for the final, and let's be honest, the easiest step. We just add our two parts together. And look at that, it perfectly illustrates our main idea. The general solution, y of t, is the system's natural behavior, y sub c, plus its forced response, y sub p. This one single equation now describes every possible thing our system can do under that specific force. Okay, that's great for one simple force. But what happens when things get more complicated? What if a system is being pushed and pulled by a few different forces all at the same time? Is there a shortcut? You bet there is. This amazing shortcut is called the superposition principle, and it all works because of a really powerful property called linearity. Basically, the left side of our equation, the part with all the derivatives, it behaves in a linear way. And what that means for us is that we can take a really complicated forcing function, break it up into simpler little pieces, solve for each piece one at a time, and then just add all the solutions together at the end. It's a classic divide and conquer strategy. Let's make this real. Imagine your total force is some combination of two simpler forces, like 3 times force G1 minus 4 times force G2. If you've already figured out the particular solutions for G1 and G2 on their own, we'll call them YP1 and YP2, you don't have to start all over again. The new particular solution is just 3 times YP1 minus 4 times YP2. It's an incredibly powerful time saver for tackling complex problems.
So, we've gone through quite a bit here. Let's just take a moment, step back, and boil this all down to the one core idea that you should absolutely remember from all this.
This is it. This is the whole ballgame. Whether we're talking about a bridge, a circuit, a pendulum, or even way more abstract things, this fundamental principle always holds true. The complete story is always two stories woven together: the system's own innate character and how it chooses to react to the world pushing on it. And that brings us to a final thought to leave you with. This really elegant idea that a system's behavior is its natural tendency plus its response to a force. It describes so much of the physical world. So where else might this pattern show up? Could it apply in economics, in biology, maybe even in psychology? It's a really powerful way of looking at and understanding complex systems, wherever you find them. Thanks so much for watching.